All right. We record here as well. Okay, today we want to talk about some negative effect for the integrator. Yeah. What type of negative effect we can see for the integrator? Okay. So this is called integrator wind up. Alright, so this will be talking about what are the negative effect, or what is the main negative effect for a derivative term. In practice, what is the negative effect for a derivative term? A derivative term in practice. What is the negative effect of a derivative term? Could you remind me?
Amplify noise.
It amplifies noise, exactly. That's the main effect for derivative term. If your sensor measurement is a sensor measurement, usually they are noisy in general in practice. So when you have a sensor, it's not a perfect, so it's noisy. Then when you add derivative, it will amplify the noise. So that's why pure derivative, it's something we cannot implement physically, but also we need to think about adding filter to filter the noise. So you need to, in your design, think about the number n. In your PID, you remember, you have this number n, so also you need to tune. This is a cut-off frequency in which you need to make sure that all the high frequency noise are cut off, and the remaining signal, the signal that you are interested on, it remains. You didn't cut it. Luckily, in general, the noise are high frequency noise, and the signal we are interested on, almost it is a low frequency signal. So that's how we can have a low pass filter to cut the noise or to decrease the noise. And in the last session, we saw the effect also of adding this filter on the response of the system. Like, if you remember, it reduces the noise, but it increases overshoot. So it has somehow some drawback. But we need to have it, otherwise the system in general will be very noisy, and it's not realizable impacts. So if we don't want to add filter, maybe we can add any other stuff just to make the derivative term realizable, so you can realize it without any consideration for the number n. It's possible, so you make your derivative, but better to make it with filter well designed to filter the noise. That's what we saw in previous session. Today you will see one drawback of the integrator itself, and this we call it integrator wind up. I put for you a link here which we will see together, talking about the wind up effect. But just before talking about it, let me introduce it to you. The wind up effect, or integral, it's for the integral. The integral wind up effect is, that's the definition of it. So when the control signal becomes saturated, like here, so this is the figure below is my control signal. If you look at the red curve, so now let's consider only the red, forget about the blue. If you look to the red curve here, we can see that the control signal is saturated, and most likely the wind up effect happens when the control signal is saturated. So that's what you need to remember. This wind up effect doesn't happen in general unless your control signal saturated. So it happens if you are using integral. If you are not using integral, it doesn't happen. In case if you are using integral and your control signal saturated, then you will have wind up effect for your integral. And we'll learn how to eliminate this wind up effect. What's the wind up effect? When the control signal becomes saturated, the integrator keep outputting a control signal to compensate for the error. the controller keep outputting what? A control signal. This integrator keep outputting control signal to compensate for the error, because the error is still there, but actually your actuator cannot speed up. Imagine it's a DC motor, cannot speed up, but you need it, the integrator needed to speed up to minimize the error. But your actuator is saturated, cannot turn more than 1000 RPM, for example, and you want it to turn more, it doesn't. So then keep adding up, outputting control signal, and keep adding till it go to 1500, go to 2000 RPM, and keep saying that, because for the controller, the controller cannot see the saturation, doesn't know that the actuator is saturated. All what he's taking as input is the error, and the error telling there is a very high error. But your actuator cannot react more than 1000 RPM. So in that case, on the output, so then I'm accumulating energy in my control signal output, the output of my integrator, I'm accumulating more energy. Then on the output, so assuming now the output reach the set point. So after some time, so here, from here, I'm saturating at here, and this is my output Y. Alright, this is my desired output here. So I'm keep increasing. So still I have error. I'm saturating. From at time 0, my actuator is saturated. So time 4, at t equal 4, I'm reaching my set point. So basically it should go in blue, but actually what happens, your output, if you wish, your output keep going up, and the control still saturated like this. Only it decrease down, it goes down when you are here, because you are accumulating a lot of energy. Before you reaching the set point, because it was saturating here. And this is what we call here, we call it the wind up effect, this overshoot here that happens. So to eliminate it, we do anti-wind up. When we do anti-wind up, we keep the saturation, but it becomes less. So here the red curve is output overshoots with standard PI controller. Here I have PI controller, you see the output is overshooting, and this is the control signal. But output overshoot removed with anti-wind up. So if I do anti-wind up, so we'll learn later on what is anti-wind up, to remove this overshoot, to tell the actuator, the controller, the integrator, you need to tell it that your actuator is saturating now. So you tell it that the actuator, so you need to feed back somehow the saturation from the actuator to inform your integral that the actuator now is saturating. So you don't need to keep providing more signal because of the error. So you have error, yes, so then, but don't keep accumulating energy. That's right, you have error, but your actuator is saturating. So doesn't make sense to keep providing more control signal and more effort, because that's the saturation. Your actuator reaches the saturation point. So it doesn't make sense to keep accumulating energy, because it's the summation at the end. So keep accumulating energy, it's not a good solution. So when the actuator gets saturated, the controller should get acknowledgement or get information about the situation of the actuator. Basically, that's what we mean by anti-wind up. So output reaches set point at t equal 4, but integrator has stored so much energy. When it is at t equal 4, it was stored so much energy, so that's why it overshoot before going down. So you see the control signal goes down at t equals 6, so after 2 seconds we have this overshoot. So that's a standard control signal. Remains saturated up to here, and here the control signal goes down with anti-wind up. With anti-wind up, if we implement the anti-wind up, when you reach the set point, which is here, the control signal goes down directly. Because you are at the set point, you don't need to apply more effort. So you start going down. But here it continues this way. So that's the effect, the integral wind up effect. And that's the blue curve is how it becomes if we implement, how it eliminated if we implement anti-wind up. And here we will see what is anti-wind up, how do we implement it in practice. Before seeing it, let me go with you with this short video. I want you to focus on his explaining to you again what I just explained, but in a better way. Okay. You have the link video at the first slide I showed you. Okay? So let's see the anti-wind up effect in this video. Alright,
branches.
So here at the beginning, he just reminding you a little bit about saturation and what we mean by saturation. Alright.
Contribute to controlling your system.
Are
We
you
started
able
with
to
a
hear
simple
the voice?
proportional controller and then added an
على
integral to
الفويس
remove the
مسموع
steady
بس
state
كتير
error.
واطي دكتور.
مسموع الفويس.
Okay, so let me make it highest possible.
And then a derivative to increase performance and to keep the system from
Better?
overshooting.
ايه دكتور.
And that seemed simple enough, and it appeared to work. In theory,
If you wish, I think we can have it in YouTube, not on the MathWork, outside MathWork. And if you can find YouTube, maybe voice will be better. This is YouTube.
in the last video, we described the PID controller and how each of the three branches contribute to controlling your system. We started with a simple proportional controller and then added an integral to remove the steady state error and then a derivative to increase performance and to keep the system from overshooting. And that seemed simple enough, and it appeared to work. In theory, at least.
So in theory, it works, but in practice, you have effect for the integral term and the derivative term, especially when you add sensors and you consider your saturation of your actuator. The saturation of the actuator, it affects the integral term in practice, because maybe now in theory you are considering there is no saturation for your actuator. In theory, maybe you are considering pure measurement of your signal or unity feedback. Sometimes you are taking it without sensor dynamics and without noise added to your environment, added from your environment. So then you don't find a derivative noise effect of the derivative term. Also for the integral term, you don't consider saturation of the actuator in simulation, but actually you can simulate the saturation. Now we learn how to simulate the saturation last time. So we can simulate it. We can add noise. We already added noise before. So then now we will learn about the effect in practice of saturating the actuator if I'm having integral term.
But there are a few problems that a PID controller introduces in practice, and in this video we're going to focus on how the integral path in particular can get us into trouble. To start, we need to expand the system we call the plant. The plant can be thought of as two separate systems. The first is the actuator or actuators. These are the devices that are generating the force or energy to change the system. A motor or a heater are example of actuators. The second system is the process, or the thing that the actuator is pushing against or trying to affect in some way. If your actuator is a heater, then the thing you are heating up is the process. So here's the problem. In real life, actuators aren't linear systems. They can't perfectly follow any arbitrary.
So he said the actuators in practice are not linear systems. What do you mean by that? What we mean by that, like your actuator is not like this. Like it's not for each input you apply, you will get output. And then if you keep increasing your input, you will get output. Like if I apply 10, maybe I get 50. If I apply 100, I get 500. If I apply 1000, maybe I get 5000. This is a linear system. There is no problem. But in reality, your actuator has saturation, maybe from 0 to 22 volt, or from -5 to 5 volt. It has saturation, so it's not linear. So now if I apply this 12 volt, okay, it's linear. But if maybe I apply an input, high input, it doesn't keep going proportional. It will saturate. So it is non-linear system. Okay, your actuator in reality is a non-linear system.
Command given to them. There's backlash and rate constraints and saturation, to name just a few. And these limitations can wreak havoc through an ideal PID controller like the one we described in the last video. So if you stick around, we're going to expand beyond a simple integral and make a few changes that will protect your system against one of the more common nonlinear problems.
So now, as we expand before together beyond the derivative term, like we said, we should not have, we expand beyond the derivative term. Like instead of having KDS, we said let's add n over s plus n, or as MATLAB describing it, 1 over s n plus 1. So you divide by n, we said last time, so then 1 over ns. Or yeah, so well, let me don't go over it, but you remember it, of course, from, so directly simply explained last time, but MATLAB is expressing it as n over 1 plus n 1 over s. We demonstrated last time. So this is, we expand, that's what we mean by we expand beyond the derivative term in practice. So in practice, but why in practice we are not taking the saturation effect then? For the, why here the PID block doesn't consider the wind-up effect in practice, just taking into consideration the noise? Well, for a reason. First reason, because we cannot realize KDS or D times S alone. That's for a reason, so we integrate it here. But however, I over S, it's realizable. We can realize because degree of denominator more than the degree of the numerator. But here it's not the case if I want to consider D times S. So that's why you are seeing it here. But if you wish to consider in your here PID block the wind-up effect, you go to here. So we never show it to you, but maybe you saw it in your research yourself. If you go to output saturation here, and you say I want to have limit at my output, like I'm limiting the output of my controller in a way to consider the saturation. So the saturation, then if you go to here, there is anti-wind-up method, and you pick the method that you want to use. Here they are putting two methods. One we call it back calculation, another we call it clamping. In your MATLAB they are implemented too. So you can choose one of the method to anti-wind up. So you consider the saturation effect in your simulation as well. So you consider the practical case. Okay. So you in MATLAB also you can do. So now he's gonna explain this anti-wind up effect for us. Simply the one I explained to you, but here in a different way.
Found in real-life situations. I'm Brian, and welcome to a MATLAB Tech Talk. We begin by looking at the path the error takes through the integral to generate an actuator command, and then through an actuator to get its response. Imagine a scenario where the actuator can saturate, or another way of putting it, where the actuator is not able to follow the command it's given. Picture this. A system is subjected to some continuous non-zero error.
So now explaining the saturation. And if you remember on Moodle, one of the assignment was, or one on the labs we did, DC motor lab, that was explaining the saturation effect. And I asked you to give me a brief 5-minute video explaining all the DC lab control and including the saturation effect. So I posted some of your solution, and among the solution, among the solution I posted, if you go and revisit them and remind what you said, how did you define the saturation? Some of you, even sometimes many of you, didn't explain the saturation well to me in the videos you submitted to me. So now he's explaining the saturation effect now. Later on, he will talk about the wind-up, integrator wind-up effect. But now he's explaining the saturation of the actuator, what it means. So those who didn't understand it, please look at it now as well.
When that error goes through the integrator, the output will continue to rise over time. And if our actuator is, say, a motor, then we can think of this value as the commanded RPM. If we command a motor with this ever-increasing request, it will spin up and follow the command at first, but eventually it will hit its maximum RPM and won't go any faster, even if the actuator is being commanded to do so. This is saturation. The motor can't run any faster. And it's not just motors that experience saturation. It's
not just motor. Almost any system has a saturation.
It's all real actuators. For example, a battery can only supply so much current, and
like a battery, for example, it saturates at a maximum current.
A speaker can only produce a sound so loudly.
Right. Also speaker, it has a maximum sound can produce. So anything, it has some saturation.
When you are developing your PID controller, if all you interact with are linear models of your system, you might not think this is a big deal. After all, there is no such thing as saturation in a linear system. Any output value is achievable, so you'll never come across this situation. You want to spin a motor at 100 RPM? 1,000? 1,000,000? This is possible in a linear system, but real-life systems are not linear, and if you only think about how your PID controller will behave in this sense, that can get you into trouble.
So now, if it's saturated, so now we understand what's saturation. So now, in real practice, you understand your actuator, it will get saturated. So assuming now you send a control signal in which your actuator is saturated. You are in a scenario where your actuator is saturated. So how your PID will behave, in particular, how the integral term will behave. Okay.
We can figure out why by asking the question, how does our PID integral handle an actuator that saturates? Assume we have the drone from the...
So now, guys, now I want you to focus on, because whatever we explained before was about saturation. So now we will explain the wind-up effect, okay, via an example. Okay, so here he will explain to you the wind-up effect. So the effect of saturation, what's the wind-up effect of the saturation of the actuator on the system itself and the dynamic response of the system. So the system will overshoot actually because of the integrator that doesn't know that your actuator is saturated and keep accumulating energy and sending command to the system to eliminate the error.
The last video, and we're trying to control its altitude with a PID control law. The altitude error goes through the 3 PID branches and then sums together to get a propeller.
So this is a simple system. You have a drone, and you know, this is a system. They separate the actuator from the plant, from the drone, and simply the actuator is the propellers, or if you wish, are the DC motor here. Here, those are your actuator in this case. And you want to control the altitude of the drone. Let's say we did one exercise before at the beginning of the term, like the altitude at 50 meters. I want to control it, so then if I put a disturbance or anything, it should return back to the 50 meter altitude.
Command. The propellers are the actuators, and they react to that command and spin up or down to some speed. The propellers generate a force that lifts the drone, the process, into the air and changes its altitude. Again, for this example, we're going to see what happens only within the integral path. But there's a catch.
So now we will focus on the integral path.
After we turn on the drone and tell it to fly up to...
That's what we want. We want the drone to fly up to 50 meters. Okay, so at this moment here, the error is, if you want to calculate the error is, assuming this is the reference altitude 0, so the error now is how much between your desired altitude and the actual altitude of your drone. How much is the error?
50 meters.
50 meters. So now the error is 50 meters at the beginning, because the actual altitude that you are measuring from the sensor here on your drone is 0. Okay, so then it will spin up to reach the 50 meters. That's a normal scenario. Okay, but what if
to 50 meters, we don't let go.
But what if I'm holding the drone? So imagine this scenario, I hold the drone. I don't let it go to the 50 meters.
We continue to hold on to it for a little while, keeping
So we keep it hold it for some time.
near the ground. I don't know, maybe we wanted to inspect the operation before letting it go. Or maybe this was a test of a construction drone that attempted to lift something heavier than it can handle. Either way, there is a constant error of 50 meters in the control loop, and this will enter the integral. And
so with time, because I'm holding, let's say, for that amount of time, from here, the x-axis is the time, for that amount of time, if this purple curve is my error, okay, the purple curve for him is the error. If the error is, if that's the error, mean during that time where I'm holding my drone, the error is keeping at 50 meters. So then the integrator, which you want to track to reach the 50 meters, will keep providing control signal to the propeller, right? The output of it, this control signal will go to the propeller to speed up. So then your drone start to speeding up, and it will saturate, and you keep holding it. Even after saturating, you will keep holding it, and you are accumulating error.
Start adding up, increasing the command to the propellers, telling them to spin faster because the system needs more force to take off. The propellers will keep up with the command, spinning.
So now, here, what do you have here? You have the blue curve and the green curve. So the blue curve is the command, it's the control signal. Okay, again, the blue curve is the control signal, and the green curve is the output, or is the RPM, like how much RPM. That's the propeller command, and here is the propeller speed in green. You see, it is the speed. You're telling him to go faster, then it goes faster, which is fine. When you tell it goes faster, it goes faster. It's still in the linear zone. But what happens if
faster to fight against you at first, but you're strong and holding it down, and since the drone isn't rising, the error is still there.
So the error is still 50.
Eventually, the integral will request a speed that is faster than the...
You get what's happening now? What's happening in this scenario?
Saturation.
Saturation, because your controller requested a speed. So you requested a speed for your drone, because at the end this speed, it will give you the thrust force to push your drone up. So then the controller requesting very high speed that your propeller is not able to provide. Then it will saturate. So cannot provide, assuming it's 1000 RPM, cannot provide more than 1000. You keep increasing because the error is still here. You are, as an integrator, you don't see the controller is saturating. This, we don't see it.
the propeller motors are able to spin and they will stop accelerating. However, the integral, not knowing that the propellers have given up, will continue to increase the command. You might think this isn't much of a problem since the motors themselves are essentially ignoring the command, so it's not like something will break if you command too high a value. But winding up the integral command in this way, or commanding a value over the saturation limit, isn't the problem. The problem comes from trying to remove or unwind the excess command.
So the problem is not by winding up over the saturation limit. It's mainly by when you go to anti-wind up, when you want to return back to the saturation. That's what happens when the problem is happening. So we'll see what he means by that.
From the integral. Let's imagine this situation. The maximum motor speed for this drone is 1,000 RPM, but we've held onto the drone until the output of the integrator is requesting
so your integrator is requesting 2,000 RPM, and if we keep holding the drone by hand, we will keep requesting more and more RPM, because for him still you have error. He's still seeing the error and doesn't see the saturation. So then he will keep requesting the propeller to spin at 2,000, 3,000, etc. until you have no error.
2,000 RPM. The motors are only spinning at 1,000 since that's the fastest that they can go. At this point, we let go of the drone.
So now, at this instant, we leave our hands from the drone. So what will happen in this case? The drone will spin at 1,000 RPM. It will spin fast, reaching the 50 meter. It will reach the set point. So when it reaches the set point, normally the error will go down. Actually, the error will become 0 at the set point.
And it rockets up towards the commanded altitude. And the error begins to decrease.
So the error becomes to decrease. So that's the error is decreasing, right?
Once the drone gets
maybe here, so have a negative error, right? Because it is so here you have 0 error. You are at the set point at that time, but here you have negative error. So what happens? Let's see what happens with the output of the propeller and the speed and the command signal. What's happened with the command signal?
Above the command, the error term becomes negative and the integral output starts to decrease.
So when this integral output start to decrease when your error becomes negative. When the error, if you wish, becomes negative, your command signal start to decrease. Start to decrease here, but in reality we want it to decrease here. So in reality it's better if my blue curve, if my command signal was like this. When it's saturated, it will saturate, and in here start to decrease my control signal, because the error is decreased at this point. Here where the error starts to decrease, so I should react here. Okay, I need to calm down my speed, because now I'm at 1000 RPM and 1000 RPM. No, actually in here, yeah, in here I want to say I want it to start decrease. My command signal should decrease from this point rather than going up this way and then decrease. So that's the wind up. So ideally when you do anti-wind up, we let it go this way rather than this way, so we see the saturation.
However, it's coming down from a value of 2000 RPM. So when it's at 1900,
So it is at 2000 RPM, the common signal at 2000, not at 1000. Even so, you are spinning at 1000 here. You are spinning at 1000. So what's
The
happening?
motors are still spinning at 1000. When the command is 1500, the motors are still spinning at 1000.
So even if your command is 1500, this doesn't reduce the error, because you're still very fast, spinning very fast. So then your drone will keep going up.
We have to wait until the integral unwinds back to a
Yeah, that's what will happen. So now
1000 RPM before the propellers actually start slowing down, and during that entire time, the drone is skyrocketing upwards and out of your sight. This is called integral windup, and it's something we need to protect against in our PID controller, because you never know if you're going to get into a situation where an actuator saturates.
because maybe in some situations the actuator will saturate and you need to protect against this one. So how to protect against this one? Hopefully the wind up effect is now clear. Let's go and see the our figure here.
Do we add a filter to prevent the signal above 1000 RPM?
So we'll see in the next slide what we do to provide to implement the anti-wind up effect.
Okay.
But for now, just understand the difference between. So that's the wind up effect that you can see. When the signal saturates, we are in a scenario where I'm having saturation. That's my dashed red curve without wind up, without anti-wind up effect implementation. Anti-wind up is not implemented. So when I reach the set point, I keep overshooting, then I return back. But if if I implemented the wind up, the control signal, that's my control signal, it's saturated, right? But once I reach here, I reach the set point. Once I reach the set point, the control signal start to decrease, because I don't. It doesn't make sense now to keep having providing high effort signal, or very high control effort. Doesn't make sense, because I reached the set point. Why I need to keep providing high control effort, saturation control effort? I don't need anymore. I already at the set point, so I need to go back. So, but if I'm not considering the anti-wind up effect, I will keep going this way. I will keep saturating. My control will keep providing saturation, because I already accumulated during this stage. I already accumulated my command signal, accumulated energy. So I'm keeping going up. I'm asking the controller to go, or the plant to go up, or the actuator to go up and up, even if I'm saturating. But in the anti-wind up effect, no, I'm telling the actuator to don't go up, to know that we are in saturation. And that's how the response will be. The control signal will be like that. You still have the saturation, but the effect of it is too much less than if you have not implementing the anti-wind up. So there is 3 ways to implement this anti-wind up. Here we'll see the first method. It's based on observation. Alright, so what we do, that's my actuator. I take the control signal. I take the control signal, which is here, V in this case if you wish, and U, the output of your actuator. And I differentiate them. So I look to the signal here. Here I call it ECES, like saturation error. Saturation. I look to the saturation error. If it is positive, if the saturation error is positive, that's mean U bigger than V. But usually this doesn't happen. Usually what happens is if the V below U max, then V equal U, and if V and U are equal, so in this case the saturation equals 0, and then this is not considered as if it does not exist because you are multiplying by 0, right? This situation when you are in non-saturation. If you no saturation, then this is if this block doesn't exist. So now if I'm saturating, V is bigger than U. V bigger than U if I'm saturating. Like for example, the controller asking to send 2000 RPM, but the motor can deliver only 1000 RPM. So then U minus V is negative. E in this case is negative. And how much is negative? This depends in the value between U and V. How much is the difference? So then this error, I multiply it in case I'm saturating. So now in case I'm saturating, I'm doing some feedback, multiplying by this error by a proportional constant that's going to adjust the behavior of my integral term. It's going to adjust it in a way to improve my response. So basically it's telling, so here because it's negative value, then at the end it's like a negative feedback if you wish. Okay, in some book you see positive, negative, and then they put here negative. All right, so it's the same. What you are doing, you are taking, basically what you are doing here, you are relaxing down the control effort coming from the integrator. So you are telling the integrator, don't keep going up. Don't keep going up. Here I'm subtracting from it with a proportional constant that we need to design. So you need to design this KAW. That's basically how to implement it. That's the first method. Okay, we know that that's PI controller if you wish, and also we could write it this way, and this is most commonly used in industry, you know. So then let's see this example of tank level process control, which it has a pump that saturates at 0.22 volt and with integrator onto wind up. Recall the response of the PI control response. That's the PI control response of my system. That's the water level. So I want to control it at the blue. The blue is the desired water level, and this is my output. That's how it behaves. Remember, we had no steady state error because the integral term. But what happened to the control signal? If you remember, it's saturated. So we have saturation actually here and saturation here. So it's saturated at 22 volt and at 0 also saturated. So from 0 to 22. So I have here saturation in here and in here and in here. So if I put the anti-wind up control response, so if I implement this one, taking into consideration that my controller may saturate, then look how the response will be improved. So I have less overshoot. So in real scenario, you may consider why this happened to you. Actually, because your actuator is saturating. So then do anti-wind up and make it this way. So all what you need to know now is how to design this additional constant. It's called KAW. Okay. They call it AW because anti-wind up. That's a symbol. You can name it any constant you wish. So later on we'll see how to design for it. But for now also you can do it for even for PID controller the same. So here we don't have space to continue the block diagram. That's why I'm feeding you like this. Okay? But here you have plant, of course. The output of plant is you. You are feeding it back up to here. So the only change is in the is in here. So how to design, how to find K, AW. K anti-wind up constant or the anti-wind up gain equal 1 over TR. And what's TR? TR you compute it this way. It's at the as an approximation. As an approximation, a reasonable compromise is to select a reset time that is a fraction of the integral and the derivative time. Integral and derivative time which you already computed for your PID controller. Okay, then TR is at the halfway between them. TR equal square root of TI times TD. Then K anti-wind up equal 1 over TR. Okay, so why we are doing this? In the previous slide, that's the rule. That's the rule. But why you are doing this? Just to understand. Here, some little bit explanation. Anti-wind up gain is commonly defined with respect to a reset time. That's how it's commonly defined, like 1 over TR. And TR, we define it as TI TD in the next slide. The integral time and the derivative time. So they are saying why it's commonly defined with respect to a reset time. We call it reset time because it's a time on which I relax down my integrator controller, the output of my integrator controller. So short reset time, if you have short reset time like large gain, the integral is reset more quickly. It's exactly as a proportional when you're adding proportion. Okay, so large gain, the integral is reset more quickly. If long reset time means small integral, small gain, so integral is reset more slowly. So it depends on you. Usually we recommend to set quickly. In that case, you want large gain. Okay, then short reset time. You can tune it yourself just by experimenting values. But as a rule of thumb, if you wish, as compromise, in case if you have derivative, so you do TI TD. Caution, setting TR too small can lead to undesirable reset when measurement noise is present. So if you put too small, so means the gain too high, as I told you, this is preferable. Okay, then you do if you don't have derivative term. But if you have derivative term, you remember one time we told to you that also the proportional term amplifies the noise. So if you have measurement on noise, if you have noise on measurement, then having high gain will amplify the noise because proportional effect also amplifies the noise. So it's not desirable if you have integral in use. So if you don't have integral, take a large gain and use. But if you have if you don't have derivative, if you have derivative in your system, then take a compromise. If you have derivative, take a compromise between TI and TD, and then so you are sure in this way you are quick enough, but at the same time you are not very slow. You are quick enough, but in a case that you don't add noise, you don't amplify the noise in your measure. Okay, that's the rule we use. Is it clear? Is it clear the anti-wind up using this method?
Yes, doctor.
Okay, let's see the
Doctor.
benefit and drawback of the on-to-wind up. Okay, the benefit: remove steady state error like PI. So remove the steady state error because you didn't eliminate your PI controller, it's still there. So that you are removing the steady state error. And benefit: reject disturbance like PI. Also we reject disturbance if we have disturbance. But here, remove undesirable overshoot. In case of saturation, you have undesirable overshoot, as you saw in the many examples, okay, like the water tank example, for example. Or so the overshoot, this overshoot is undesirable, so it will remove it, so it becomes more robust system. However, you have the drawback that you're still saturating, but this helps. Like, remember, the saturation is not too much, but still saturated. But you have little bit more complexity to implement the system. Those are mainly the drawback. So you see, when you implement the on-to-wind up to my water level tank, I'm less overshooting, still saturating, but the saturation effect is less. Okay, so here no overshoot or very less overshoot. Okay, compared to here. In here, high overshoot. Alright, so here I have overshoot and the saturation is much more. Okay, this is basically about the first method. And the method we saw in our lecture is the back calculation, not the clamping. Basically, here you can see it in MATLAB. If you go to the PID controller, it's a block. When you go to the description of just each component what it is about, I went basically to the on-to-wind up method. And if you have two methods, you have none, means don't use any on-to-wind up mechanism. Just simply use saturation block. PID, you click on it, so you can just use saturation block and without any on-to-wind up. If you don't want to put the saturation block outside, like here, then you can use it inherently here. Take the saturation block in something or something, 5 minus 5, and then apply, and you will see it here. So then instead of using it outside, and say none for any saturation, any on-to-wind up. Otherwise, you can use the back calculation. In this case, we complete the back calculation coefficient, as you saw in the lecture, or the clamping, which we didn't see in the lecture. Clamping. What is the clamping? Basically, clamping is about just to clamp the integrator, like to cut the integrator off. That's what clamping is about. So in our video, we saw here where this one expanding beyond simple integral. Here in our video, he's talking in details about the clamping approach. Okay, so you can see how it's implemented. And in the lecture, I explained to you the back calculation. The observer approach is this when you take observer. So this needs some state space knowledge if you wish, and how to design observer. So this is not required, just know the clamping and the back calculation. Also, observer approach is not implemented in single for PID. That's how it is basically state space control. So in case of you are building observer in advanced process. Clamping here is explain in details, but as I said, this is about turning the integrator on. That calculation is the one we use. So if you go back to the PID block, and here they are explaining to you what is it what is the integrator wind up effect and why we need to eliminate it, as we described in the lecture and also in the video. So in both cases, sometimes as in the video we show us like the sign of the output signal never changes. Like for example, I'm keeping having error, but maybe it could not be the case like here, for example. So the sign, because my reference signal changed, so my output signal will change in the sense. So maybe so sometimes the error keeping this way, sometimes I go down, so I'm here and I decide to go down, so my output, my input level go down, so my output will go down. So if I'm in this scenario, or I'm in a scenario where I'm keeping always constant, okay, keeping constant this way, like here, I'm in a scenario where I go and keep going like that, or no, in a scenario where I change. So in both scenarios, it's unwanted effect when I have separation. When I have separation, it is unwanted effect. So in either case, controller performance comes up. So I recommend you to read it as we explained in class. When you select the limit output and the weighted sum of the controller component exceeds the specified output limit, basically like you are telling in your PID, don't normally read things they talk about PID, and you put what you do, you put a limit for your PID, the separation limit, when the weighted sum of the controller component, like here the summation inside the PID, remember what you have the three blocks P, I, and D. Then you added to them a controller here, a saturation block here. So the output is bounded, but here is before the saturation block is not bounded. So when this weighted sum exceeds the specified output limit, so what happens is the block output halts at the specified limit because you are adding saturation block. However, the integrator output can continue to grow, and that's what we call integrator growth, increasing the difference between the block output and the sum of the components, and the sum of the block components, okay, before the separation. In other words, the integral signal in the block can be unbounded even if the output appears bounded by the separation limit. So that's the integral signal is unbounded. Here it's unbounded because without a mechanism to prevent integrator wind up to resolve adversely. If you don't have a mechanism, back calculation or clamping or observer, for example, method, the certain method which is not defined. So without this mechanism to resolve adversely, if the sign of the input signal, actually in a while, like the water level, if this never changes, keep going this way, so the integral continues to integrate and overflow. So you have overshoot. Overflow value is the maximum or minimum value for that type of integrator output. Like it could go for maximum overflow in the maximum sense or negative sense. Overflow value is the maximum or minimum value for the data type of the integrator output. Well, here in numerical analysis, with numerical analysis, at the end you have some saturation, some data on which you cannot go up. Each register into the computer can hold some data, some big value. After it, you overflow, or maybe it's like unfinished. Consider as unfinished. Something cannot hold it in your register. Well, this is not necessary. If the sign, so I told you, if the sign of the change, once the weighted sum has grown beyond the output limit, it can take, so it changed down. For example, as I give you the example of the input signal, which is changed down. As I give you example in the water level tank, and the example in the video, when it change when you leave the hand from the drone. So it can take long time to unwind the integrator and return the weighted sum within the block separation, within the block separation. It takes time, and in this time the signal will overshoot. As the video explained to you, here, yeah, as you can see here, and the video, so it takes time, and our first slide. So it takes time to return back, even if we reach the set point. Like in here, we reach the set point at 2, but it keeps going, so the water level it keeps going up. Because the control signal here, the pump voltage output saturation is not the same as the common before it. It's the pump voltage here, which is the pump voltage, which is here. What you are seeing is here, not there. If you are not implementing the pump going up, so you are seeing V. Okay, here's the correction. Here the point Q, and here the motor voltage. Okay, then V and U is alright. Then this is V, and when you implement the going up, pump voltage, and it's the pump voltage. Okay, so the pump voltage, it doesn't matter what you call it, V or VU, it doesn't matter, but essentially the signal here, if you are saturating, the signal here is higher than here, and keep going higher and higher. You have lot of signal. Then to correct it, when the water level went down, or when you are reaching the set point, so the error becomes 0. If they don't show you the error signal, if they show you the error signal, you will see here that the error becomes 0 at this point, between desired and actual water level. The error is 0 because before the saturation block, the command is so higher than the limit, then the output still saturated. So that's why you can see here it takes some time before it will go down, because once it's here, so then the error starts to go in the negative side. Then your actuator will start to react now, and therefore you have this. So then, this because you don't control the on up, and as we go back again to the video, so it will keep commanding even for high saturation. And therefore, when the error becomes 0, so from here you start going down. That's starting going down from here, and in the case of clamping, for example, clamping, you start going down from here. Then you will go down from up. So it takes time, and you will be having overshoot. So this amount of time that you are taking leads you to overshooting the output signal. So here in this graph you cannot see the output signal, but here you can see the output. That amount of time, from 2 to 4 point something, the output keep going up because it's accumulated energy before. So that's the output keep going up, and then it return back. But at this time, if you look at this time here, to the common signal, which is in here, you see it start to decrease down at time equal 2 seconds. Time equal 2 seconds, and immediately start to decrease down when the error is 0. But you already accumulated too much energy, and this too much energy, so now so that's right, the common signal is going down, but you are still saturating. You are still saturating because you are already above the saturation limit. And that's right, you are going down, but you're still above, so that's why you are in here, in sounding. And then, so that's why you are overshooting. In this time from here to here, from 2 to 4, you are overshooting. Then later we start to decrease. So this is how to avoid by implementing the auto wind up clamping. Simply just clamp when you are saturating. Don't take the integral effect, just don't take integral at all, take it out, or doing what we call back calculation method, the method we showed you in class. So this is the back calculation method. Unwind, as explained here in MATLAB, unwind the integral when the block output saturates by feeding back to the integrator the difference between the saturated and the unsaturated control field. The following diagram represents the back calculation feedback circuit for a continuous time control. To see the actual feedback circuit for your controller configuration, they are telling you can right click on the block and select mask, look under mask. For example, here they are telling you if you want to see it in your MATLAB, you go to mask and look under mask. And here they put the as a picture example the integrator they implemented, which are familiar with 1 over S. But our concern is just want to look onto the onto wind up. You can click here, and so here for example, because I'm saying none. Okay, so if I want to have back clamping, for example, so now if I look under mask, so it will take the back calculation or clamping, partial clamping and so on. So this is the one we implemented it just to feed the KB. Alright, this is the method. Use the back calculation parameter KB to specify the gain of the onto wind up feedback circuit. It's usually satisfactory to set KB equal to 1 or so here it's important point, KB you put it to 1, or for controller with derivative action then use KB equal step PID. Otherwise you may put it 1. It's satisfactory enough. If you have PI controller, use it, put it 1, it's enough. Back calculation can be effective for plants with relatively large dead time. What we mean by dead time, plant with dead time basically is just like when you give an input, it takes time to get to the output. It will get my input, maybe it will delay a little bit before responding. Okay, this delay, we call it dead time. So some plants they have this delay, and in reality many plants they have this delay. Super responsive. This we call it dead time. So is effective for plant with relatively large dead time. However, clamping is not as good as back calculation if you have dead time. For large dead time system, it can lead to poor transient response. Okay, Clamping, basically just to cut off the integrator. And when you want to cut it, here is explained in details. I'm not explaining to you the clamping method, but you could still use it in MATLAB actually, technique clamping. And but I'm not explaining here is the explanation, and you can read it here how it is going. So basically, you need to see the differences. You need to see the differences. If you look at it, you see the differences here and see the sign. You need to check the sign between the input of the controller and the output of the controller, and maybe also the output of the integrator. Not the output, not so the output of the pure block PID. You need to check the sign between the output of your PID block and the input of your PID block. Take the sum and check them if they are same or different. Then according to that, you have a logic gate that you switch your clamp to 0, means there is no integrator to take it out, or to here, like so you switch your clamp to on off. Of course, all your decision, this and this go up to here, is a result of this and this. So, and this is what this is the difference between whatever you have in the separation of input output. Basically, this step is similar to the step we did in here. In addition, for clamping on-off integrator, we do a sign and AND gate. We don't want to go in details. You could see it yourself on the video.